Everyone. Okay, recording. So welcome to ICON's seminars, and at each week, each Friday, 3 o'clock, we'll host our seminars. So our seminar organizers, Ziran, Wang, and Patrick and To, they have spent a lot of efforts in inviting the most excellent researchers, especially outside Purdue and inside Purdue, to give seminar at ICON. And on robotics, autonomy, machine learning, IoT, physical AI, and all kinds of hot topics. And especially today, we have invited Dr. Yongxin Chen from Georgia Tech. Yongxin is also a very nice friend of mine. And he received his PhD from University of Minnesota, then joined Iowa State and faculty, and then joined Georgia Tech and the faculty. Now you are associate professor.
Yeah.
And Yongxin's research is in control theories, machine learning, with application in robotics. Dr. Chen is really a rising star in our field. He has received many prestigious awards, such as Best Paper Award from Attribute Transaction, Automatic Control, which is perhaps #1 journal in control theories. And also Best Paper Award from SciEM Journal on Control Optimization. He also received the ASF Career Award and also the Ekman Award, which are given for outstanding young engineer in control field. So really outstanding person and academic researcher. So he will give a talk on stochastic diffusion for control, inference, and learning. So station is yours.
Thanks for the invitation and for the introduction. It's really a great honor to have the opportunity to speak at the very famous Institute of Control, Optimization and Networks. And also thanks for attending the event. I've never seen so many people in my seminar before. Today's topic is about stochastic diffusion. So stochastic diffusion is a very powerful mathematical framework. It's also a secret weapon I use in my research. So I would like to share with you how these tools can be used in many different areas like control, Bayesian inference, and machine learning, and through my own research experience. Okay, and feel free to stop me if you have any question. So the basic element of this mathematical framework of stochastic diffusion is Brownian motion. So Brownian motion is a concept which is it's a very powerful concept. Basically it has gone through a sequence of work and to reach the level we see today. So the first person, I would say, the first person who started to work on this area is Brown. He is a biologist. So what he did is
Let's share that screen. You share different screen, so the online people don't see the.
Oh, they cannot see this?
Yep.
How do I do that? So they see something different?
Yeah, the PDF one.
Or you can say research share at the top of the screen.
Let me see. Okay, something is going to happen. So you're seeing this one. Oh, so let's start. Okay.
Stop share. Yeah.
Okay, stop share.
And then you share the.
It's a control problem, so I should basically doing the right topic.
I should have to desktop problem.
Yep.
Is this a
We see yours and then the in-person.
you see the same thing?
Yes.
Okay, so I should continue. So where we? Okay, so we are here. The Brown, he was the first person who actually studied this subject. What he did is he observed a very strange phenomenon. So basically, the pollens on water surface, they behave in very strange way, which cannot be explained in any regular mechanics. So that's basically laid down the foundations for other people to explore this area even further. The second giant in this area is Einstein. So in 1905 is his miracle year. He published one of the 4 papers he published. Actually, give a comprehensive explanation of Brownian motion. Basically, he explained what is the reason for Brownian motion. And later, the next key person is a very famous mathematician and also control theorist. So what he did is he developed the first rigorous mathematical theory for Brownian motion. And that's why Brownian motion is also known as a Wiener process these days. And this subject was further developed by Kiyoshi Ito. So he developed this notion of Brownian motion into a full subject known as stochastic calculus. So he is the founding father of the subject. And that's why whenever you learn stochastic calculus, the name is Ito calculus. So because he did that. So let's see a few pictures to understand better what the diffusion process looks like. Okay, so this picture here is just a simulation of a two-dimensional Brownian motion. You see, I don't know where is the starting point, but you see the trajectory is irregular, so you cannot observe any pattern. It's just something completely random. And this figure tells you the evolution of a one-dimensional Brownian motion. So this is the time, evolution over time. So this is the trajectory. You see it has a very strange pattern. So no regularity. And this is actually what the Brown observed. Okay, this is actually what the Brown observed in his microscope. So this yellow thing, you can view this as a pollen. And this black point, you can view this as water molecules. Basically, the pollen is behaving in a very strange way because of the collisions, irregular collisions with the water molecules. So after so many years of development, so this very simple physical phenomenon has been developed into this subject known as a stochastic diffusion, which is what I'm going to focus on. And it's a very powerful tool. It can be used basically in any place when you have uncertainty and randomness. And one very good example I like to use is the stock market. And it's quite random. So if you follow stock market, you'll see what I mean. So how to model such a very strange behavior, irregular behavior? So it turns out the answer is known as the stochastic differential equation. So it looks like this. This is the stochastic differential equation. So it's very much like a differential equation. So the only difference is that you have an additional noise term. So if you don't have this noise term, this basically reduced to a differential equation. It tells you the change of your variable is controlled by two components. One component is the drift, which is the differential equation part, and another component is noise. So if you don't worry about the notation too much, so one way to understand this is really, if you simulate this process, what you do is it's more like a simulation for ODE, but you put the additional Gaussian noise to this. It's a very, very intuitive thing. And but because of this additional term, the calculus for this type of process is very different. And a very fundamental difference is the Ito's lemma. So basically, if you have a function of this stochastic process, when you take a derivative, when you take the differential of this, you would get this term. This term here is the standard, okay, is the standard differential equation chain rule. But you have the last term, and this last term is really caused by the noise. Okay, we will get back to this type of phenomenon later. But this one thing to keep in mind is that there's a huge difference between stochastic calculus and the standard calculus caused by the Brownian motion. And because stochastic process is pretty random, so sometimes if you want to understand the behavior better, sometimes you need statistics. So you need to know the distributions of the variable. So that is how the Fokker-Planck equation will tell you. So if you have this differential equation, you know xt is going to be random. And of course, the distribution is also going to change over time. It turns out, even though the process is random, but the marginal distribution of the state can be captured by a deterministic PDE. So this is the Fokker-Planck equation. It tells you how the distribution of the xt should change over time. So both the original SDE and the associated Fokker-Planck equation are widely used in application and also in this research talk. Okay, and this is the outline of my talk today. So basically what I'm going to do is I'm going to explain several of my own research which utilize stochastic diffusion in control the state distribution in modeling the high-dimensional data distribution and in sampling from the posterior distribution in Bayesian inference. So the focus is going to be the second one and the third one. I'm going to only just briefly mention the first one, okay? So let me start with the control problem. So it's an interesting class of control problem. So in this problem, what we are trying to do is we are trying to control the distribution of a dynamic system from an initial to a target. So for instance, like this. So this is just an example here. So you have a dynamic system. So the initial distribution is supposed to be, let's say, a bimodal distribution. And I want to do something to make sure after some time that the state follows a terminal distribution, which looks like this. So this distribution can represent the uncertainty in a single dynamic system. It can also be used to model the collective dynamics of a, let's say, robot swarm. So it's the same framework can be used in both. You just need to interpret your distribution properly. And you see this problem is really you want to move one distribution to another distribution. And this resembles another very famous problem in mathematics known as the optimal transport, where the goal is to move mass from one distribution to another distribution, like in civil engineering. Okay, so based on the connection between this optimal transport and also stochastic diffusion and also this problem formulation, we basically develop a framework to solve this control problem. Okay, and when this problem is used for a single dynamic system, okay, then this can be used to effectively regulate the uncertainty in our dynamic systems. For instance, in the spacecraft landing problem, and in spacecraft landing problem, your goal is to make sure your aircraft doesn't land too far away from some specific area. So basically, you want to regulate the uncertainty over there. By using this type of covariance control framework, you can have a better control of the uncertainty over there. It provides a more direct approach compared with other traditional control method. And when these distributions, we talk about here models, the collective dynamics or the group behavior of collection of systems, then you can use this to control, for instance, the robot swarm. So it's one framework can be used in both. So let's just see more concretely what we are doing. So this is a very concrete example, a special example known as the covariance control. So what we did here is we have a problem. So the dynamic system is a linear dynamic system where the control is corrupted by noise. So dW is the random noise and the U is your control. What we want to do is we want to drive the state from an initial Gaussian distribution to a terminal Gaussian distribution, okay? And in the meantime, we want to find the control strategy that minimizes this, this control objective here. So you see, this is very, if you have ever taken linear control course, you see this is very similar to a standard linear quadratic regulator problem. So the only difference is that now you have an additional constraint on the terminal state. And also you don't have a terminal cost. Because you have a terminal constraint, so it doesn't make sense to put a terminal cost because it's going to be a constant anyway. So that's the difference. So how do we solve this problem? So it can be viewed as an untraditional linear control problem. How do we solve this problem? It turns out the solution is very similar to the standard LQR problem. And what happens is that in standard LQR problem, what you would have is you have to solve a Riccati equation, which basically looks like this, which goes backward in time. So it turns out for this problem, you have to solve a coupled Riccati equation. So you have two Riccati equations, pi and h, and the pi goes backward in time, just like the standard LQR theory, and h goes forward in time. And these two Riccati equations coupled only through the boundary. You see, this differential equation only depends on pi, this only depends on h. They're only coupled through the boundary condition, okay? So that's the difference. So in control, we really like the Riccati equation. So, but in standard linear control problem, you just have the first Riccati equation and also the terminal, the boundary condition is given by the terminal cost. So that's why you can solve this directly. But here, because they are coupled, you have to find other way to solve to get a boundary condition. So it turns out that you can actually solve this coupled Riccati equation system in closed form. And after that, the solution is just like the standard optimal control. Okay, so this is just a simulation to show you under optimal control what is going to happen. So here, what we want to do is we have a linear system and we have an initial Gaussian distribution. And our goal is to drive this to a terminal Gaussian distribution. And this is the trajectory simulations, which under the optimal control we obtain. You can see it's really just a contained inside the level set of the distributions of these two covariants. So this is for the linear system. Linear system, you just need to care about covariance control. In general, nonlinear system, you need to do a little bit more, right? Because if you are not a Gaussian, you need to worry about high order moment. And sometimes to the extreme, you need to worry about the entire distribution. And this, in the general problem formulation, this is what you want to do. You have a linear system, but it is a nonlinear control system. Okay. And what you want to do is you want to drive the state from an initial distribution to a terminal distribution. And you want to find one control that would minimize this cost. And it turns out that this problem is a generalization of the previous one we just discussed. It turns out that this problem can be reformulated as an inference problem and this connection. So I'm going to skip the detail here. But this connection and also the connection to stochastic diffusion and the optimal transport will give you an entire framework to solve all of this problem. And nowadays, this problem has found many applications in different areas. For instance, if this distribution is used to model the uncertainty in a single dynamic systems, you can use this to control small size system. For instance, the flap wing aircraft, because this is the type of systems you really has a significant uncertainty. Okay, you can also use this to do robust motion planning and even probabilistic MPC. And when this distribution is used to model the collective dynamics, then you can use this to do formation control and many other things, like a multi-object tracking problem. So there are many things here, and I know also there are some ongoing work even at Purdue that is based on this framework, and we're really happy to see this going on. And this is basically the control part of the story. And next, I'm going to move to the machine learning. And the thing I'm going to discuss is diffusion model. It's a emerging tools in generative AI. So what is a generative? I need to. I learned one thing today. What is generative AI or generative modeling? So the setup is very simple. You give me a lot of samples, which you assume from one distribution, okay? But you don't know what that distribution is. Then what I need to do is I want to model, I want to reconstruct distribution. And more importantly, I want to generate new samples from this distribution. So this is a good example. So for instance, I give you 1 million pictures, okay, which I believe follows certain distribution. What I want to do is I want to train a huge neural network. And the final goal, what I want to achieve is I can generate a new sample from this neural network so that it looks like the original pictures. But it's beyond memorizing, so it should be new pictures, but which follows the same distribution. So this is basically the standard pipeline for generative AI. And this is a very standard diagram for generative AI. So normally, what you learn is called a generator, okay, which is a huge network, which may have millions or even billions of parameters. What you want to do, this generator to do is the generator is going to take something very simple, Gaussian random variable, for instance, but it's going to output a random variable which follows your data distribution. So this means after you train this generator, you just need to take a random sample in, then you can generate very realistic pictures, which is cool. So over the last decade, there have been many different frameworks for generative AI. It's a big area in machine learning. So for instance, like a generative adversary network and a variation autoencoder. So recently, the two most popular generative AI is one is the autoregressive model, and another one is diffusion model. So autoregressive model is the backbone of the large language model. So all the large language model are based on autoregressive model. And but the focus today is diffusion model. Almost all the pixel-wise generative AI for computer vision is based on diffusion model these days. So diffusion model is very young. It's only, let's say, about less than 5 years old, even younger. So, but it can already achieve amazing performance. It's the main framework for computer vision generative AI. So you can use this to do many things. For instance, you can use this to generate image from text. So for instance, this picture is I think the text is a raccoon is playing a guitar. So we know this is cannot pattern, it's fake, but it looks so realistic, and so we assume it follows the same distribution. So this is what generative AI can do. We can also do some tests here. Let's see if I can show you something. Just, oh no. I want to, how do I? No, it's fine, it's fine. I think I found it. So you can play with this. It's just there are many resources. One of this open source one is the Stable Diffusion XR. So you can just input whatever you want and just generate some picture. For instance, this is what I showed in my class last week. A raccoon is playing a piano at the Times Square. So you see, it just generates something quite realistic. So I can input something like now. Purdue University Law. In, let's say, early February. Let's see what can this do. You see, this is what the Purdue is supposed to look like in early February. But today it's like an outlier. So you see, and it also looks like it. I'm not sure if, because I haven't got a chance to see the campus. Does this look like Purdue? No, it looks like a campus at least. And the weather-wise, it looks like Purdue. So you can do many things. You can play with this to get some hand-on experience. But this is an open source model. So the model owned by Google and this type of non-open source one, they even have better performance. So let me see. Okay, so this is one of the major application domain of this diffusion model, text image. People start to make a lot of money out of this. And of course, you can do many other things. You can do like a picture editing. Okay, like in painting, if you have an old picture, something is cropped, you want to complete this. And of course, this is just a special case of this very general problem called inverse problem. So basically, you can use this to solve any inverse problem to some extent. So that is a very exciting thing. And one of this problem is the PDE solver. So people are trying to use this type of diffusion model to solve high-dimensional PDE. I believe there's some ongoing work here. I'm not following that topic that close. And more recently, people start to use this for robotics application. Specific one we are talking about is robot learning. So in robot learning, what you want to do is you want to collect a demonstration, and then you want to use this demonstration to train your policy. I'm talking about imitation learning, not reinforcement learning. So one major bottleneck there is the data is very expensive. You don't have enough data. So, but the generative AI can really generate fake data, which looks quite realistic, and then use this to help your training. And they have really achieved a great performance. Okay, so for instance here, the first row is I think only these two pictures are real data. All of these are fake, but it's really very difficult to see whether these are fake data or real data. And when you use this for robot learning, it can really do a good job in data augmentation. And also there are many things, other things you can do. So these days people start to use this diffusion model to generate a 3D structure, which sometimes is very important in computer graphics and also robotics. And people even start to use this in video generation. Maybe pretty soon you will see a movie made by generative AI. So there are many exciting things going on. So it's also developing very fast. But back to the real basics of this diffusion model It's really this equation over here. Okay, so a diffusion model consists of two processes. One process is the forward process. Okay, so this is called the noising process. So what you do is a linear stochastic diffusion process. Okay, this is the noise term. And this process would do one job. It keep adding Gaussian noise to your data. And eventually, after some time, your data really looks like noise. So this process would take your initial data to a Gaussian noise. So that's the forward process. It looks like this. So initially I have a picture which is realistic. Then after I stimulate this forward Gaussian process, you see after some time it becomes pure random noise. Okay. So then there's another process which is the inverse of this process. It's called the backward process. And this process, it looks very similar to the forward process. I also have the same component, except for one additional component known as the S theta. It's the neural network. Just think this is a big neural network. And our hope for this, the backward process is, first of all, the backward process runs backward in time. And what we hope this to do is you start from a Gaussian noise, and after some time, I would be able to generate real data, which looks like this. I start from Gaussian noise, which looks like this. Then after some simulation, you see I see more and more clear feature, and eventually I generate data distribution. So how do we make sure this can generate the distribution I want this to generate? So that is basically by connecting these two processes, we can do that. We know the first process would do what? The first process would take your Gaussian noise. No, the first process would take your data to Gaussian noise. The second process, the goal is to take the Gaussian noise to data. So if we can just reverse the first process, right, we can do our job. So from mathematics point of view, what we really need to do is we need to make sure the backward process and the forward process, they have the same trajectory. If they have the same trajectory, just like you run the process backward in time, then of course, after this is done, you can generate the data distribution. And how do you achieve this in practice? Okay, how do you achieve this in practice? Does this show up again? How do we achieve this in practice? So as we said, what we need to do is we need to make sure the forward process and backward process, they share the same trajectory. So what we can do is we can denote Q as the distribution of the forward trajectory, and the P, which depends on your neural network, as the distribution of the backward trajectory. Then what we need to do is we want to make sure they match, they're equal to each other, right? Once they're equal to each other, we are done. So this gives us this loss function. So what we want to do is we want to match P theta and Q. So you can minimize a certain distance. So this actually just KR divergence is one type of distance. So this is the one objective, but this objective is very abstract because what is this, right? So it turns out there's an easier formulation for that. So that is based on the theory. It turns out there is an ideal solution to the backward process, which is the gradient of log Qt, where Qt is the distribution of the forward process. So if you take the S theta to be this process, then you can make sure, you can prove theoretically that the backward process is equivalent to the forward process. And this formula was actually first developed in the control community by Bill Anderson, actually. This is the formula. So this would lead us to this.
You mean Brian?
Yeah, Brian Anderson, your advisor. Yes, so it's in a very old paper, like 40 years ago. But then this will give us this objective because we know the optimal solution is gradient of log Q. So what we have is a neural network. So what we need to do is we want to develop a regression cost. We want to make sure this is very close to this, right? But the problem of this loss function is that it's not trainable because this Qt is the distribution of the xt, which something we don't have access to. But through some very simple transformation, you can actually reformulate this objective function into this denoising score matching. Okay, and this basically means, and this is equivalent to this. And in this new objective function, what you want to do is you sample data from your data distribution, then you sample xt from your forward process, which is a linear process. You can do this right away. And you need to make sure the distance between your state and the gradient of log qt, this term is the conditional distribution of the forward process given x0. Because the forward process is a linear process, therefore this qt xt given x0 is a Gaussian. So this one has actually closed form. So this term is a trainable. So, but if you just don't worry about the details, but basically this is a very easy trainable, scalable training loss. And this is the only loss function used in other diffusion models, okay? So at the end of the day, for any diffusion model you see, at the end of the day, it's about this. But you train this with different large network, then you can do many things. Okay, so we are not going to worry about the training part of the story, because sometimes it's very expensive and you have billions of parameters. But let's go to the inference stage. So let's say some big company, they train a huge network, S data, which S data is already given to you. As a user, we want to use that, right? If we want to use that, what we want to do is we want to stimulate the backward process, right? We start from Gaussian noise, we stimulate the backward process, and we hope this to generate the data. So this is what you want to do. You sample from Gaussian noise, then you simulate this process backward in time, okay? Then when you get x0 is a very realistic sample. But of course, this is the SDE. How do you even solve this? So a very naive approach is the Euler discretization, because for continuous time process, you cannot solve this. So you have to discretize this. So this is the Euler discretization. It has an additional noise, but it's a very naive discretization of this one. And you just solve this. It turns out it's very expensive to solve this to high accuracy. So in the original paper, okay, when they did that, they have to kind of do a discretization step to 4,000 steps. That's very expensive because at every step, you have to evaluate the network with, let's say, 1 billion parameter. You have to do this 4,000 times to generate one picture. It's not very efficient. So our motivation is, so this NFE means the number of discretization, number of function evaluation of the neural network. It's basically the number of discretizations. So our motivation is to reduce the computational cost when you use a diffusion model. So how do we do that? How do we do that? It turns out there are many approaches that you can achieve this goal. We actually propose 3 different strategies in our work. So due to the time constraint, I would only focus on the first one, and I would briefly mention the second one. So the first one, what we did is we developed a better discretization scheme for this backward process to generate new samples. So this algorithm still is the best training-free sampling algorithms for diffusion model. So this is the basic idea. So first, this is the process we want to simulate. This is the backward stochastic differential equation. It turns out you can convert this into an ordinary differential equation. This is something we are very familiar with. It's the differential equation, it's just a derivative, this is equal to that, okay? So one can prove that these two, they share the same marginal distribution if your S data is very accurate. I would skip the detail. It's based on this Fokker-Planck equation I talked about before. But just trust me that if you can solve this ordinary differential equation, you'll be able to generate really good samples. So how do we solve this ODE? There are tons of algorithms you can use, right? So of course, the first algorithm everyone will try is the Euler discretization. So what you do is you discretize this, you assume this is the constant over time step, and then you just calculate the next step to be the previous one minus this. This is the naive Euler discretization. So it turns out this algorithm is not very effective, actually. The main problem is this term here changes really, really fast as t varies. And this would induce a large discretization error. So can we do better job in solving this ODE? That is how expertise comes in. So if you take a closer look at this ordinary differential equation, even though it's a nonlinear differential equation, you see this S theta is highly nonlinear because it's a huge network. But you have this first term, it's actually a linear function, right? So if you have a control background, what we can do is we can view this ODE here to be a controlled system, which linear control system, okay? With feedback control being your neural network, which is huge. It's like a linear control with the controller modeled by a huge network. Okay, how do you make this discretization faster, more efficient? So we know if you have this linear control system, what we can do is we can write down the closed form solution. So you can actually prove that this is the closed form solution. This is the value at the next time point is equal to something multiplied the value at the previous time point, then plus this big chunk. And this is, of course, this is a closed form. This is not directly implementable. So this is just the formula used to solve a linear control system. And this phi here is known as the transition matrix, which has closed form in this setting. Okay, so this is what you have. This is closed form, but this is not implementable directly because you have this integration. But if you take a closer look, right, if we assume this term, which is your control, to be a constant over a small time interval, then basically you can take this term out. So if I assume this to be a constant over a time interval, I can take this term out. So then I get my update loop to be a linear combination of the previous value plus this function evaluation. And this is really just a zero order holder used very often in control system when you want to discretize a linear control system. Okay, so it turns out this method can achieve much better performance. And of course, when we do this zero order holder, right, we kind of assume that the control S theta is a constant over the time. So this assumption sometimes is not that reliable. So sometimes you can have that's a linear approximation or polynomial approximation. This can give you better performance. This is known as the first order holder or high order holder. So it turns out if we do this, we get something called, we basically try to approximate this function using a polynomial. And with all these components together, we get an algorithm which can generate high quality samples from any diffusion models with about 10 steps. So that is at least one magnitude better than all the existing methods. And this is just to show you what happens in practice. So this is just one example, one qualitative example. What you see is the first column is the standard Euler method to solve that ODE. You see, if I use 20 steps, it's a disaster, and 50 steps is not very good. After you use 200 steps, it starts to give you reasonable result. And our algorithm is the last column. So you see, even with 9 steps, we can already achieve very good result. This one is comparable to this one. And this plot here shows you our algorithm for a standard benchmark example. And our algorithm is the green curve. So this means the performance at the different number of discretization steps. And the FID is just some evaluation metric, the lower the better. So you see, our algorithm is significantly better than the other algorithms, especially when the number of steps is relatively small. Okay, so this is about this algorithm. So yeah, that is, I want to bring a comment here. So this is one area I'm trying to push is, so I want you to see that through this example that control actually can do many things for machine learning. And this is a very nice example. In control, we have a lot of tools and that can be used in machine learning. This is one thing. So I believe there's one area called the machine control for learning, which is very promising. It's basically we can leverage control tools to solve different learning tasks. And this is a very good example. Okay, then the next one is a acceleration via parallelization. I'm not going to get into the details, but what we wanted to do here is we want to generate very large content with very small diffusion models. So very often, let's say if you want to generate these very large pictures, or you want to generate the animation, which is very long. It's very expensive computationally or data-wise. Computationally, because you need a huge model, and data-wise, it's very expensive to collect this very long horizon data or this large picture, because I believe you have never seen a picture like this that long, right? So it's very expensive. So how do we achieve this goal? So our strategy is we kind of train very small diffusion model. Each diffusion model is just in charge of a small piece of this. Then you can piece this together in a very smart way. Then you can generate very large content. And that is our strategy. And this strategy turns out it can give you really reasonable performance. And this is basically some performance you see. So we use this in computer vision task. And so we can generate really large content, even though our training data is really this small. And another very interesting application, which I have no time to get into details, is one task in imitation learning, in robot learning. So in imitation learning, if you want to use imitation learning to do, for instance, long horizon type of task, it's very expensive because human demonstration for low horizon task is very expensive to collect. What we did there is we collect a lot of skill level, very short horizon task. That's very cheap because you can just do one thing, then you can record this. So you don't waste the whole thing. And what we did is we use diffusion model to model each of the skill. Then we use this idea to piece them together. And then we found a way to effectively use this type of small diffusion model to do long horizon task motion planning. So right now, this is one of the best algorithms for the robot learning for long horizon task motion planning.
Quick question.
Yes.
So this is more like for the long picture, right? You want to generate. Is it possible that the picture is not so long but also wide, and then if the
It's possible.
with the algorithm to just generate one piece of them, but there will be coordination in like in the length and also the other.
You can do both. It doesn't have to be long. It can
Okay.
be huge. You can do this 360-degree depiction.
see.
Doesn't really
Nice.
matter. Yeah.
Thank you.
Okay, so this is about the diffusion model. How am I doing with time?
15 minutes.
Okay, this is about the fun stuff. So the last topic I'm going to talk about is more serious. It's a bit heavy, so let me just let's see if we can go through this. This is another topic I'm really interested in. It's called sampling. Okay, what is sampling? So the task of sampling is very standard. What you want to do is you give me a distribution, which you already have the closed form. What I want to do is I want to generate a sample out of this. For instance, you give me a Gaussian distribution, I want to generate a sample. That's very easy. But if you give me a very complicated distribution, then it's very difficult for me to sample from this. So this problem has been widely used in many different areas. For instance, uncertainty quantification, which is very crucial in almost every areas in engineering practice, estimation and sampling, reliability analysis, design optimization, and the molecular dynamics, and there are many others. Okay. So Markov chain Monte Carlo, or MCMC, is one of the most powerful framework to do this job. So the idea is very simple. You construct a Markov chain, which is a random process. Then you simulate the Markov chain. And you construct the Markov chain so that this Markov chain has a stationary distribution, which is your target distribution. So you just need to simulate this long enough. Then you hope the sample you generate follows your target distribution. So this is a very, very powerful framework, actually. So I like to use, there's one code I like very much. It's basically MCMC can be used almost everywhere. And also I believe so. Okay. So what is exactly a sampling? So if you are familiar with optimization, then it's much easier to see what is a sampling. So you are given an objective function, f, okay? So in optimization, what you are trying to do is you want to get the minimizer of f. That is a standard task. Everyone knows optimization. In sampling, what you want to do is you want to generate a sample from this distribution, e to the power minus f, okay? Which could be very complicated. So you see, compare with optimization, sampling has the advantage that in optimization, you only have the minimizer, which is the optimal solution. The sampling not only give you the optimal solution, it also gives you a lot of suboptimal solution so that you can quantify the belief or uncertainty in your optimal solution. So it has many advantages over optimization. And of course, it has also many disadvantages. One of them is the computation. It's much more expensive to do sampling. Okay, so that's one connection between optimization and the sampling. Another connection between optimization and the sampling is you can view sampling as a distribution. No, you can view sampling as an optimization problem, but it is over the space of distribution. So to see this, what we can do is, you see, your eventual goal is to generate a bunch of samples. Let's say if I denote the distribution of my samples to be mu, what I really want to do is make sure the mu is equal to pi, right? Because if mu is equal to pi, basically I generate sample from the target distribution. Therefore, this is a very reasonable objective function. Basically, you want to find a distribution which is equal to your target distribution. So this is the distance between your real sample distribution and your target distribution. So this connection between optimization and sampling is really the driving force for new algorithm development for this sampling over the last many years, not many years, just several years. I'm going to show quite a lot of formulas in this problem. This one is good. This is called the Langevin diffusion. Okay, so I think more than 80% of the sampling algorithm is based on this process, for the Langevin process. So it looks like this. It's a special stochastic differential equation. You have this Brownian motion term, but the drift term is very special. It's equal to minus the gradient of this. Okay, so if you don't have the noise term, this is the gradient flow widely used in optimization. But if you have this noise term, it turns out this process has a very special property, which is that the target distribution, which is e to the power minus f, is equal to the stationary distribution of this Langevin diffusion. And moreover, under really mild assumption, you can prove the distribution of the state is going to converge to my target distribution. So which means if we stimulate this process long enough, I would do a good job to draw random samples from my target distribution. So not only this process is a feasible choice, it's actually one of the best option, but I'm going to skip the explanation here. It's basically, it turns out this process, Langevin diffusion, can be viewed as a certain type of a gradient flow of the sampling problem. So that's not worry about detail. And this process has a really fast convergence rate under mild assumptions. And this is good. This basically means if you can simulate this Langevin diffusion, you can do a really good job in sampling. But this is a continuous time process. So back to the same question, right? If you want to use this in computer, you can never simulate continuous time thing. You have to discretize this. So how do you do the discretization? So of course, we can again use this Euler discretization. So which is basically you discretize, this eta is the step size. So if you do Euler discretization of that process, you get this one. So it's like a gradient descent, but driven by another Gaussian noise term. This is good. It's very simple to implement. Everyone can implement this in like 3 lines of code. But the problem is this discretization is not good. It has very low accuracy. And one reason is that the stationary distribution of this process is no longer your target. So you have to choose your step size really small to make this happen. So it's not a very good choice. So the question we ask at that point is, if this is not good, what is better? Can we have a better discretization scheme for this Langevin diffusion so I can use it for my sampling task? And we draw inspiration from the optimization community. So in optimization, you have another algorithm called the proximal point algorithm. So in optimization, you have gradient descent algorithm, which looks like this. But you also have something called the proximal point algorithm. You basically iteratively solve a bunch of optimization problems. So this proximal point algorithm can be viewed as a backward Euler algorithm for discretizing the gradient flow. So the question we ask is, if it's so nice, can we develop a proximal point algorithm to discretize the Langevin diffusion so that we can have a better sampling algorithm? And it turns out the answer is yes. And the answer is actually very simple. So this is the algorithm, which is a bit busy here. But the key idea, let me explain the key idea. So what we want to sample is e to the power minus f. Okay, that is our goal. So what I did is at first augment this distribution into a distribution of x and y. So originally is a distribution of x, now is a distribution of x and y, joint distribution. But one very nice property of this distribution is the marginal distribution of this over x is still my target distribution, because at the marginal, you just need to take this integral over dy, you find out this reduced to the original one. So this means if I can sample from this joint distribution of x, y, I will be able to sample from my original distribution. So this looks like a very silly idea because you are trying to sample from a distribution in a large space. But because this is a joint distribution, you can do something called Gibbs sampling. So Gibbs sampling, basically what you do is you fix x, you sample from y, conditional on that x. Then you fix y, you sample from x. You iteratively do this, okay? And the classic theory already tells you this is going to converge to your target distribution with no bias, which is really good. Of course, there's a catch here. So you can say this very easily, but the implementation is not easy because if you fix x, you sample from y, you fix x, so this is just a constant. So it's a Gaussian distribution, it's very simple. But if we are fixed y, if I want to sample from x, basically is this one. You fix y, so y is just a constant here. Now you want to sample from this distribution. So this is another sampling task, right? So how do you develop efficient algorithm to sample from this? It becomes another issue. So, question?
So I think why like physical constraints, so you fix y, so this constraint, but if you also sample y, that
I don't quite understand. So what's the constraint on the distribution?
you have your target distribution and you have like a physical constraint.
Yes.
You also sample from this.
Yes, that's a good question. Sampling from constrained distribution is much more challenging. So here I would focus on unconstrained distribution. If you have constrained, that is another big open problems, which is ongoing research. So it's so compared with optimization, I would say the sampling is still in a very early stage. So still right now we focus on unconstrained sampling. So it's still quite far away from constrained sampling. Okay, is that okay?
Yeah.
Okay, so that's good. Someone is following. So the reason, okay, so you see this step, if I fix y, I want to sample from x. This step looks very much like a proximal operator, which is the getting the minimizer of that. So that is the reason we call this algorithm proximal sampler. So this proximal sampler is a special case of Gibbs sampling. It has asymptotic convergence, but for algorithms, we don't really, we need more than asymptotic convergence. Asymptotic convergence means if you wait long enough, you are going to converge. But if you do algorithm design, you want the convergence rate. You want to characterize how fast will this converge. So this is the one open question here. Another open question is open question at that time. Another question is how to sample from this conditional distribution, which would name this RGO efficiently. If we can solve these two problems, we will be able to sample from our target distribution efficiently. So let me quickly resolve these two issues in this talk with no details. So the first one is how fast this will converge. The second one is how to implement this efficiently. So in sampling, these are the standard assumptions. So of the potential F. So the first two correspond to convex and convex optimization. The last two correspond to non-convex optimization. It's actually more complicated, but these are several standard assumptions used in sampling, which people care about in most real practice. So it turns out the algorithm we have, if we denote log kx to be the distribution of xk at the case iteration, okay, then you can prove that the distance between your iteration to your target converge linearly, because this is the exponential function, right? K is the number of steps. If you assume the target distribution is strong convex. And this would match the result for proximal point for Stirling convex function. That was already proved in this paper, which proposed this proximal sampler. One of our contribution is we improve the proof convergence in general settings. We are able to characterize the convergence property of this algorithm and the general assumptions like convexity and this type of more general conditions. And we characterize the convergence rate. So when this is convex, you only have sublinear convergence. So that is very standard in optimization. You only have sub convergence. If you have this LSI, some type of condition, you can prove this function value converge to the minimal linearly. So this corresponds to some optimization people call PL condition or gradient dominant. So if you have work on reinforcement learning for LQR problem, you may recognize this condition. So this is the correspondence there, and there are some other conditions. So this convergence results are tight, which means you cannot improve this further. So that's the convergence. So these are really good convergence property because they're fast. So the last question I want to briefly discuss is how do we implement the sampling task of X conditional on Y? So just recall what we want to do is I fix the Y. I want to sample X from this distribution. So there is a very clear trade-off here. So this eta here can be viewed as the step size for my overall algorithm. So if you want your algorithm to converge fast, you want the large step size. The larger your step size, the better. So you want the large step size because the overall algorithm can converge fast. On the other hand, you want this eta to be small because you see if eta is very small, this term is going to dominate, right? So this fx doesn't matter. And this term dominate means what? This distribution is very close to a Gaussian. It's very easy to sample from a Gaussian. So small eta means this is closer to a Gaussian, means this is very easy to sample from. So we developed an algorithm called the approximate rejection sampling algorithm, which I'm going to skip the detail. It's a very interesting algorithm. It has been a mystery for some time, but we proved the complexity for this. Basically, the conclusion we have is we are able, with this algorithm, we can sample from this distribution with one step or constant number of steps. So it's O1. If we choose its step size to be 1 over L square root of D, and the L is the smoothness of my function. So if I assume F is to be smooth. So if I combine this implementation and the convergence result we just had, we get a very interesting sample complexity bound for MCMC. So if we assume a target potential to be smooth, and if we assume this to be Stirling convex, let's say, then if we choose the step size to be this, then we can conclude the algorithm, the proximal sampler we proposed, can sample from my target distribution with this many steps. It's L divided by alpha multiply square root of D. So it's a kappa square root of D.
So you're using rejection sampling here. Wouldn't it be a better idea to use MCMC to sample from here? Because isn't rejection sampling like you waste a lot of samples in that compared to MCMC?
And that's a very good point. So the key is really the step size choice. So if I choose a very large eta, yes, you need MCMC, but then MCMC is going to do better. But there's another strategy is to use a very large eta and use MCMC there, but you would run into some other issues. So it turns out that this strategy is the best one to get the best complexity result. But some people try the other one. So anyway, come back to this algorithm. So basically, our algorithm has complexity is kappa multiplied square root of D. So in optimization, the gradient descent, the complexity is kappa. So here is kappa multiplied square root of D. So it's not a dimension free, but it's the best complexity result we have. So at this point, this proximal sample is the best MCMC algorithm. And that's basically the end of my talk. So the key takeaway I want to give you is that diffusion model, or not diffusion model, stochastic diffusion is a powerful tool in science and engineering. And I have shown you several examples of how this can be used in control, machine learning, and inference tasks. And I believe there are many more. things can be done. And these are some of these papers which are mentioned in this talk. And finally, I would like to thank my collaborators and my students who make this happen, and also my sponsors. And finally, today is a special day, so happy Lunar New Year. Yeah, thanks.
Thank you, Yongxin. It's really a great seminar. So we will have maybe a brief Q&A section, and then the topics and in networking.
Can you hear me?
Yes.
Cool. So this is a great talk. Thank you very much. So my first question is about denoising score matching. Because you mentioned you're trying to match two distributions and trying to make this as a chainable optimization. So are there any connections between this technique and other like other distribution distance metrics like